Hello, seekers. Welcome to While We Exist. I hope all of you are doing fine, enjoying your time. But grab your seatbelts, bitch, because today we are going to talk about science. I hope the message is clear. The aim of today's podcast would be to talk about science and more specifically, astrophysics and cosmology. Uh, but who we have on the panel here tonight? Me, a curious mind um, who's interested in science, my co host, Rhythm Jain, Masters in Physics, and Rahul Srinivasan, who is doing PhD in astrophysics. A lot of heavyweights today. So, tell me, guys, how do you feel to be here?
Dude, yeah, man, it's cool. This is my first ever podcast to be in one. So I've seen a lot of big celebrities do it. I've seen DeGrasse Tyson do it, so I'll try to make
Oh.
him proud.
Yeah, this is your chance to explain science to a noob.
Oh yeah. No, I'm more worried about saying something wrong and then having it corrected and then having it not about. Yeah.
Oh, don't worry. Rhythm, how
Mm.
do you feel? Well, how do
I
you feel
mean,
about today's discussion?
I have lost touch in physics for like quite some time, so this will be a good refresher.
For sure, for sure. Okay, let's dive deep, right straight into it.
Yo,
Uh, so let's first start the discussion with this question. I have this question for you, Rahul. What is astrophysics? I mean, if we want to explain it to, let's say, someone in the audience who doesn't know anything about it, what is astrophysics? And the study of cosmology about. What is it?
Okay. Well, so astrophysics is I mean they both sound very similar and I didn't know the difference till like the fourth year of college. But basically, it's all about the scale. So the astrophysics is usually it has to do with relatively small scales when you look at it the grand scheme of the universe. It refers to specific objects within the universe, such as
okay,
stars, galaxies, congregation of matter, units of matter, where we can describe the physics behind them, and therefore the term astrophysics, astro because they are in space, and the physics behind them. But then when you look at
Okay.
cosmology, you're looking at the grand scheme of things. You're looking at the whole universe in one shot. So you're describing the macro specifications of the universe. How fast is it expanding? Is it expanding? And things like that. That will apply to all points in the universe and doesn't necessarily talk about a specific, cluster of mass or cluster of matter.
okay.
So that's basically the difference, the scale.
Okay. So astrophysics is basically a study of all the things which are in space, the materials, all the things. Did I put it correctly?
Yeah, it's the study of objects in space.
Objects in space. Yes, yes, yes.
It's loosely putting it. But the way
Okay.
I think of it is any congregation of matter and describing how that exists. So this could be stars, black holes, galaxies, supernova, anything, any phenomena that exist in space. And it's very particular to that particular coordinate in space.
Okay.
All right. All right. All right. Uh, so if I can ask, what is the current state of astrophysics? What are the things that we are working on towards right now?
Oh, okay. So within astrophysics, we have so many fields, but I guess astrophysics has had a steady uh, interest in the electromagnetic spectrum, and by that I mean signal we get which is from light, basically. All right. So things like uh, any kind of photons that we observe. This could be because of X-rays, gamma rays, or visible light, radio waves, microwaves. So they all come under the broad classification of light. And this is how we were understanding the basic astrophysics right up until, we finally had gravitational waves, which you can think of as looking at the same thing, but in a different um,
Filter.
with different particles in, for example. So you have photons, which let you look at the universe in terms of light, but then you also have these particles that may or may not exist, which basically carry these gravitational waves. And that's another way to look at the same universe. And ever since we detected them, a lot of interest has been generated in that field of gravitational waves. And beyond that, we've also had this multi-messenger astronomy,
Okay.
which is where you combine both gravitational waves and light, and you detect something with both on the off chance that you do that. So, for example, you can have these two massive stars which are extremely dense. They're called neutron stars, and when they collide, uh, they will emit gravitational waves.
Okay.
But also, they'll emit this flash of light, which is called a kilonova, and lots of energy, and that's the energy that we can observe in the electromagnetic spectrum. So it's basically when you have both these kinds of ways to visualize the same thing, that you end up getting a kind of a multi-messenger way of understanding this. You have multiple messengers here.
Okay. What
Yeah,
was
so
the name? What was the name again? Multi-messenger?
yeah, multi-messenger astronomy. Sorry. So you
Okay.
have many messengers,
Okay.
and here the messengers are, the electromagnetic waves and the gravitational waves, and
Okay.
we get information from both of them, and then we try to understand something better. I would think that this anything to do with multi-messenger astronomy or the electromagnetic waves from the cosmos or gravitational waves are basically the three major things that we look at right now currently.
Okay.
So I understand that gravitational wave astronomy was a recent development we had with new uh, LIGO interferometer. I think it's interferometer, right? Yeah. So
Yeah.
yeah. So, but I had a few questions regarding that. So, first of all, does gravitational wave and electromagnetic wave they both travel at the same speed, or like just for a layman, is or they do pass through the matter? Obviously, light cannot pass through the matter and stuff like that. But does gravitational wave pass through the matter, or do they have weird effects like lensing and stuff like that? Yeah.
That's a good question. That's a loaded question there.
Okay.
So to answer your
If I can just stop you for 1 minute before you answer that question, can you? I'm pretty new in this domain. Can you explain how are gravitational waves produced? What are they exactly?
oh, sure. Yeah.
Yeah.
So gravitational waves, the way to think about them, that the way I understood them, is to understand that the first thing that we need to understand is this whole universe, all matter, including me and you, we exist in this three dimensions of space, which is the x, y, z coordinates, or basically we have 3 degrees of freedom.
Mm-hmm.
While we also exist in time. So the way we visualize it is 3+1 dimensions. Basically saying that we live in something that has space and time. So we live in a space time.
Mm-hmm.
And this space time can be thought of as a fabric.
Mm-hmm.
And the reason we want to think of it as a fabric is because when we have massive, or basically any objects with mass, which accelerates in a specific way, such that you have a non-zero term in some complicated expression,
Okay.
you have the emission of gravitational waves. And these
Okay.
gravitational waves are basically ripples on that space-time fabric.
Okay. So
And what
this is because of the effect of mass on that space-time fabric.
exactly, yeah.
Okay.
So it's the effect of mass and energy
Okay.
on that space-time fabric. So one concept to remember is that mass and energy are interchangeable. They're probably the same thing. But if you have that, one will affect the other, and vice versa. So
So
gravitational waves are like a ripple that travels on the space and time. Basically, the way we observe it is that we see two objects. When a gravitational wave passes through them, we see that the relative distances between the two objects varies,
Okay. Okay.
okay.
and it causes a contraction and expansion in the space and the time. So that answers your questions about about what gravitational waves are.
Yeah.
And how do we detect? How do we detect them is another question altogether. But basically, we expect to detect them from very massive objects. Although they're emitted by all objects, they can be emitted by all objects. They're just too faint. So you need something very big, moving at very high velocities, for you to actually observe them.
How
And
big are we talking about right now? Is it planet big?
well, we're actually looking at stellar
Stellar
size.
objects. Okay.
Yeah.
Okay.
So we can have massive stars which are orbiting in binary systems, and technically we should be able to detect them. We can't yet, but we should be able to. It's possible for us to. But what we do detect is even more compact objects. By compact, I mean the density is very high, and they're also very, very heavy. So the heaviest and densest materials we can think of are basically black holes, which are
Okay.
not materials as phenomenon that exists within the space-time. And when
Yeah.
you have black holes that collide or encircle each other, you have very large objects,
Mm,
very compact objects,
mm.
and traveling at pretty high velocities. And that creates ripples that are very, very large relatively. And it's something that we can detect and we have detected.
Okay.
Uh, so that's how we do we. So this was a prediction from the general theory of relativity.
Wow.
And Einstein did this in, I think, 1917 or whenever he put out that paper.
Mm.
And 100 years later, or less than 100 years, in 1509-14. So that's the 14th of September in 2015. It's a very famous date in all of astrophysics. We detected the first gravitational waves.
Wow. So what
Right.
Einstein actually theorized in 1917 or 1919,
Yeah,
we were able to actually detect it in 2015.
that's right.
Wow.
This is a direct, completely comprehensive proof that at least some predictions of general relativity are true.
Okay. Wow.
So,
Yeah. Yeah. Sorry, Rhythm. Yeah. Your question, what was that?
so Rahul, my question is basically, first of all, so I understand these are perturbations created by very dense objects. Each matter or every matter can create such waves, but only very dense and very large can create enough that we can detect them. So my question is this wave, whatever you call the gravitational wave, is this only in 3 dimension or in 4 dimension? In the sense, is this these waves travel in space-time fabric or just space?
They
Hmm.
cause distortion. All right. So they travel through space-time just like everything travels through space-time.
Okay.
Even if you have a
Okay.
stationary object with respect to some inertial frame, even in that frame of reference, that object is traveling through space and time. It's just that the
Okay.
spatial coordinates are not changing, but the time coordinate has to change. Nothing can stay stationary in time.
Hmm.
Uh, while also being stationary in space. But so therefore, everything travels through space and time. But it also causes a distortion
Yeah,
in both.
that's what I mean. Yeah.
Yeah, so yeah, it indeed distorts both space and time. However, we don't really expect to detect the time distortion that much. It's very, I mean, it's very subtle.
Yeah.
So, and I don't even actually know that. So maybe I shouldn't say any further beyond that. Actually, that's something we've not really thought about. So I'm assuming it's not something very practical to probe, but we can detect the spatial, distortions that it creates through these interferometers. And I think you had asked me. Oh yeah. So a very important question you had asked me was that whether the speed at which we have these gravitational waves and these electromagnetic waves, which is light, how do they compare with each other? And that's a good question because general theory of relativity, it predicts that both of them, because they are massless waves, I mean waves that propagate through massless particles, they must travel at the very speed of light, as long as they're traveling through vacuum. And we try to test this, and we tested it to, I think, 10 to the power, like 1 in 10 to the power, with certainty. The false alarm rate, as we like to call it, is basically a measure of uh, how uh, how uh, how likely is it that by chance they happen to have the same speed. And
Okay.
that comes to be 1 in 10 to the power 15 or 14, which is a ridiculously small number. So for all observational reasons, they probably do travel at the same speed.
So basically, no amount of information like stated by special and general theory can travel more than speed of light. So and gravitational waves are no exception to that.
Exactly. Absolutely. You're right.
Okay.
Yes.
So one more question, like I'm sorry, just a small question. So is gravitational wave a proof for a particle like graviton or not?
See, this is something where I stray away from my field. But this is like particle physics. And honestly, I have no idea, but I'm pretty certain no one's told we've detected a graviton. But we have told that we have detected a gravitational wave.
Gravitational wave.
So perhaps detecting one encourages us that the other exists, but I guess it's not a very direct observation. Maybe it's an inferred observation. So
Okay.
however they do that, I guess CERN or some people like that, the particle physicists would know. But I'm pretty sure we haven't exactly conclusively detected a graviton, if I'm not wrong.
Okay, understood.
Okay, all right. Uh, Pretty fascinating information shared by Rahul there. But you mentioned black hole.
Yeah.
So let us come to our next section. Uh, so basically, first, initially, I have two questions for you regarding black hole. First, if you can very briefly explain to a, a guy who doesn't know about black hole, what do they mean? How are they formed? Second, now this is a very personal question. We all know that black holes don't emit light, right? They don't reflect light. Now, even light can't pass them. So they're essentially dark, black. How do we detect a black hole then? What is, how do we do it? So
Uh,
yeah, these are my two questions to start the
yeah, that's a good
discussion.
question. I mean, once Einstein predicted the presence of black holes, people were like, how do they form and how do we detect them? So this kept us awake for a while.
Okay.
To answer the first question, how do they form? They form predominantly because you have stars which are very massive, and at the end of their life cycle, they have to die, and the way they die is they've used up all their stellar fuel, the
Okay.
fuel that they use to create fusion reactions, which
Okay.
powers the star. So it's the engine of a star. And when that
Mm-hmm.
engine loses its fuel, it's no longer able to produce this kind of energy that keeps it bright and also that keeps it a sphere, and rather
Okay.
than implode because of its own gravity. So the
Hmm.
moment you
Okay.
switch off that radiation pressure, as it's called, basically the kind of the pressure that you have because you have this light that is being generated, which is energy that's being generated. When you switch that off towards the end of its life cycle, gravity takes over. And when gravity takes over, the star starts to collapse.
Okay.
And spherical collapse. And what happens is as they get smaller and smaller, you're getting the matter density keeps increasing.
Hmm.
And at a certain point, uh, you basically progress from being a star to being a black hole. You have multiple stages in that cycle. You perhaps
Yeah.
make a star depending on your masses, but you will create a black hole if it's a massive enough star. And that
Okay.
black hole is basically the way general theory of relativity looks at it is it's a singularity in the space and time. What that means is, singularity in mathematics, for example, is a point where the singular point x is a point where the function basically explodes or it goes to infinity or it
Yeah.
goes to, I don't remember. But the point is, though, it's basically a point where the function does not behave correctly.
Hmm.
And the reason we call that a singularity in space-time is because the space-time is not behaving correctly, because at that point, at the very center of the black hole, what we call the singularity, the density of matter is infinite. According to
Yes.
the general theory of relativity, all the matter is comprised into a volume of 0 meter cube. And because of that, your density goes to infinity. A general rule of thumb in physics is that we don't like infinities in life. We
Hmm.
usually believe good observations has told us that we've never detected an infinity, so it's a singularity. That's
Okay.
the whole story behind how a black hole is formed. You have a star that collapses. And your second question, which you must remind me again, what was it? It was
How do we detect a black
oh
hole?
yeah, good question. So how do you detect them? That's a good one. So we first detected them indirectly. You're absolutely right by saying that black holes don't emit light. By their very definition, they are black, which means they do not emit light.
Yeah.
They absorb light, but they don't emit them. In a way, it's a black body. So how do you detect such an object? Is you infer its presence. You can't perhaps directly visually detect them, but you can infer that they exist because of the way they affect the matter around them.
Hmm.
And
Okay.
that's because black holes are basically heavy objects,
Yes.
and
Yes. Yes.
heavy objects, exist like if you put it in a room full of some gas, all
Hmm.
that gas can start getting congregated inside that black hole.
Yeah.
So
And then what you can do is you can observe those gas particles go inside. So it's called a
Hmm.
accretion.
The way they
So
interact with their surrounding is proof of their existence.
exactly.
Gravitational waves and everything,
so
they
I
will produce it. Yeah.
think
However, so an important clarification to make is that what I described is an indirect way to detect black holes, where you
Okay.
look at how it affects the stars around it and things like that. So that you look at the fact that, oh, a star seems to be orbiting something, but it's nothing, and therefore you're like, oh, that must be a black hole. That's why we can't see it. That's an
Okay.
indirect detection.
Okay.
direct detection is the gravitation, and that we
Gravitational waves.
So,
so separate them both. Yeah.
so Rahul, to add on to that question, correct me if I'm wrong. I think Nobel Prize in Physics for 2020 was awarded for indirectly finding or detecting a black hole at the center of Milky Way. Is that correct?
Uh, from the center of the milk, I don't actually remember if it was for the Milky Way or something, but it was along those lines. You're right. Yeah.
Well,
In fact,
vaguely remember this. Yeah, sorry.
yeah. But I mean, for example, for the detection of the gravitational wave, we had a Nobel Prize in 2017,
17.
and
Yeah.
that was
Okay.
given to three major scientists who were there, who helped design this interferometer that we said that detects these gravitational waves. These are they call LIGO. It's called the Laser Interferometer Gravitational Wave Observatory. It's basically the device that helped us detect these gravitational waves, which prove the existence of black hole, and also was another feather in the hat for the general theory of relativity.
So, like you said, that one way to detect a black hole is by observing other stars or planets orbits around it, and we by orbit we can calculate maybe what is the gravitational attraction and what is the size, and if a very huge star is orbiting around something that is not visible to maybe light, when you call that means there has to be something that is the proof for black hole in a way. Is that correct?
Yeah.
And
That's
accretion
totally
rings.
exactly. So you have these accretion, like you said, they're accretion rings. So when something is
What are
by
accretion rings?
I
I
should
don't
tell
know.
you.
Yeah.
Accretion is basically the word accretion itself means it's something where you're gradually, well, I don't know, it's not a Merriam dictionary definition, but it's basically taking in material. All right, the way I
Okay.
see it. So,
Okay.
and when you have a black hole, it's again a very massive object, and it's going to have a large gravity. So what that means is that matter would
It
start.
sucks matter, does
Yeah,
it?
it's something matter. And the thing
Okay.
is that matter does not just come in radially because they usually have some velocity. So they kind of do
Mm-hmm.
this kind of a kind of a spiral inside.
Okay. All
So you
right. All
have
right.
a lot of gas. All that gas basically ends up looking like a dosa. And that dosa at the center is the black hole, but the dosa itself, the rings of the dosa are basically what is called the accretion disk. It's a
Uh,
disk where things are being absorbed in.
Okay.
And like I said, if you observe accretion around nothingness, or at least it looks like it's nothing because you don't see anything in the center, yeah, that's a very good very good smoking gun that, oh, there's a black hole there. There's mostly a black hole there. And a team of scientists did that. They did that very thing. So we look at we look at our own galaxy, and like you had mentioned earlier, we found that there should be a black hole at the center of it. And the reason being, we see all these stars, right? They seem to be circling,
Yeah. Okay. All right.
and we're not really sure what they are, what that was. But we never took a snapshot of the center. It's very hard to do that. So we were never able to see if it's a black nothingness or if there's something else there. Maybe it's a very big star. I don't know. But then we finally did that. We looked at a galaxy very far away. It's called M87. And that galaxy, we took a snapshot at the very center, and we did see a circle,
A circle. Okay.
everything surrounding a black circle. And from that, we were able to predict, is the mass consistent with what the accretion rate is and things like that. And things were pretty consistent.
So do we have a black hole in the center of Milky Way also?
Yeah, we have a black hole in the center of almost every galaxy.
Galaxy. Okay. All
Yeah.
right.
So I vaguely remember this, that while as black hole are very very dense and very compact objects, they are very 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 dense objects. So to actually see that there is nothing at the center and the accretion disk, we would need the size a telescope at size which whose the size of the lens of the telescope itself is the size of the Earth to actually get that resolution. So
Yeah, absolutely.
yeah.
Yeah, that's the coolest thing. Actually, they did that.
But they actually did that by
yeah. So they had a bunch of telescopes. They didn't create one big telescope.
Okay, there are a bunch of telescopes.
Exactly, but they had a bunch of telescopes all across the circumference of the Earth while it rotates, and they just kept taking snapshots. And you kind of like, they did this amazing amount of data processing, and so much of data. It was said that they actually had to fly all the data from one point to the other physically through the plane, because that was faster than than transmitting it through the internet. So they would
Internet.
actually all these data,
Oh,
they would fly it around. And anyway, yeah, so they did this amazing amount of interferometer. They did this crazy amount of data processing, and they did that very thing. They made it an apparent lens. The lens was apparently was in effect the the size of the Earth, the diameter of the Earth. And yeah, you're
wow.
right. That's the coolest thing. I was so surprised to hear that that actually worked. Yeah.
Yeah. Wow. Black holes are definitely fascinating. And to anyone, so it's not easy for a human brain to comprehend what a black hole is. Like if Earth has to turn to a black hole, it basically means to compact the all Earth into, let's say, a thumbnail, right? That is what,
Yeah, pretty
if a
small. Yeah.
normal brain has to
And
understand what black hole really means.
absolutely. Absolutely. Yeah.
Yeah. Wow.
And yeah, it's quite insane. It's insane to think about how dense that material should be.
Okay.
It's
Okay.
So, so Srinivasan, can you tell more about what exactly is your area of research? So
Hmm.
maybe
oh,
we can, yeah.
Yeah.
absolutely. Yeah, yeah. So right now I just started my PhD, so it's like this is all tentative. I hope that this will be the final research thesis, but I'm working on understanding the stars that form the black holes that we detect. So I want to understand uh, the nature of these stars. How big are they? What
Okay.
are the masses? What is inside them? What are the elements inside them? It's called the metallicity, but we want to understand that, and all that stuff that contribute to these very big black holes that we detect in from gravitational waves, and the relatively small black holes that we detect from X-rays. There's a bit of a
Hmm.
discrepancy that goes around that, and I'm trying to understand, what are the black holes that create these two different types of, what are the stars that
So we
create these.
have two types of black hole. One super big black holes, and the other ones are small.
Well, actually, if you're going to look at how black hole masses are classified, we have, I think, three or four. So we
Okay.
have something called stellar black holes.
Okay.
These are black holes with the mass of, in the order of the mass of the sun. So it's like from 5 solar masses. A solar mass is the mass of the sun. So it can be
Okay.
5 times the mass of the sun to about 80, 90 times the mass of the sun. All of these black holes are grouped together and they're called stellar mass black holes, which means that they're comparable to the mass of the sun, loosely speaking. And then you have something called the intermediate mass black holes, which are black holes which are heavier than that, something like a few hundred solar masses or 100 solar mass, all the way up to about 1 lakh solar masses, 100,000 solar masses. And they do exist. We think they should exist. We haven't detected a lot of them, but we expect them to be there. It's called the intermediate mass black holes. And then beyond that is what is the stuff that's in the center of the galaxies. They call the super
Okay.
Supermassive.
black
Super
holes.
massive black holes.
Yeah,
Okay.
it's very
Okay.
funny the names, but yeah, that's what they are.
I always like the names physicists give to their objects, whatever
Yeah.
discoveries they do. Yeah.
No, I speaking of which, the Higgs boson, right?
Higgs boson. Yeah.
So I mean, it's called the It was termed the
God
God.
particle. God's particle. Yeah.
Yeah, but in reality, it wasn't. If I'm right, this is something I read on the internet. But Peter Higgs, or the people who theorize this, they call it the goddamn particle because they couldn't.
God damn.
Oh shit.
It's just that you can't. So then it gets appended. I'm not really sure if it's true, but it's a fun. It's a fun
Yeah.
story to
They
believe that it's true.
always come up with good names. The cool names are
Yeah.
always the science ones I've seen. Okay. All right. Um, should we conclude the discussion of black hole, or do we have any
So,
other
We can keep going
questions?
so
on
I
and on.
think
Keeps on going.
I think yes, I think we can ask a few more questions because I think right now Srinivasan has barely talked about the size and the location of the black hole. Maybe you can share some interesting phenomena about black hole, like why exactly, apart from just being black, what is interesting about them? Yeah,
Oh,
like
dude, yeah, absolutely.
Yeah.
Okay. So yeah, okay, wait, I should perhaps tell you what is it that characterizes a black hole? Like how do we define a black hole, right? It might be black, it's a hole, yeah, sure. But then how do I distinguish between one black hole and another black hole? And there are three basic parameters we look at. One is the mass, which is quite normal. I say big black hole, small black hole, makes sense. And the mass is related to the radius, so we don't consider two different things. One implies the other. So you have the mass, and then you have the spin. So these black holes could be spinning. So that also characterizes them.
Okay.
And then the third one is the charge of the black hole. They could have some, a positive or a negative charge. And this isn't
Charge
something.
of a black hole. What do you mean by that?
Yeah, so black holes can technically have, theoretically, they can have charge. So just like how you can take a battery and charge a capacitor, and the capacitor on one plate has some charge, the other one has the negative charge. Similarly, you can technically have a black hole which has a net charge. Like, actually, Rhythm and I were discussing this when we were in bits tumkunta. Let's be clear here. So anyway, so we were discussing this thing where you could, a Van de Graaff generator. It's a thing that Mr. Bean had kept his hand on and had all that, his hair stand up. Basically, it's a device that lets you deposit charges.
Okay.
And if you built a big enough Van de Graaff generator, then you can keep on depositing charges theoretically into the black hole. But then the problem is, first of all, we don't have such a big Van de Graaff generator to create such a big amount of charge. And also, astrophysically, we don't expect them to exist. And we've never detected. So basically, mass and spin are the two parameters that we look at.
Mass and spin.
Yeah. So something interesting about black holes, huh? Well, black holes are basically the near perfect definition of a black body. They don't emit anything, but they absorb everything you throw at them. And so there's a lot of interesting physics that has been done using statistical physics, thermodynamics. Stephen Hawking was somebody who worked in that. Penrose worked in that. But speaking of Penrose, though, one of the most important, interesting uses of a black hole, something that we could potentially, take from a black hole instead of just observing it, is something called the Penrose process.
Okay.
Which, interestingly, was done in Interstellar. So in the movie Interstellar, if you guys remember, the whole reason behind why Matthew McConaughey died, why did he sacrifice, or he supposedly died, was that he let himself go inside the black hole. And the reason he did that was to basically deposit some energy in the form of kinetic energy, which is basically, velocity, the speed that you give. He gave all that speed to the heroine, Anne Hathaway. So he allowed Anne Hathaway to escape the pull of the black hole by letting himself go inside the black hole. And it's basically trying to take advantage of the process called Penrose process. Where if you're in
process called
Penrose
process.
Yeah, named after legendary scientist Sir Roger Penrose.
I think he was the one who won Nobel Prize last year.
Oh, yeah, that's right. Yeah, he did. You're right, absolutely. Yeah, Penrose did win the Nobel Prize last year. So this is one neat way in which you can actually use a black hole. You end up slowing the black hole down slightly, and in return, you get to take in some energy.
You get the kinetic energy of the black hole.
Damn. Yeah, you can. And you link shots outside the.
I saw maybe a video of this on some Kurza Gezat in a nutshell. That is an amazing channel, by the way. But that guy, I think, explained that you can use this in a way to extract the energy, or maybe use this as an engine. A black hole can be used as a very advanced civilization can be used as a source of energy.
Absolutely. It's a near infinite source of energy. So for us, at least. So that's the coolest thing I can think of.
By the way, I wanted to first want to just take a step back. I know that neutron star is basically just neutrons. It's neutrons and protons. In a very large cocktail. I exactly don't know how they are, but yeah, from what I understand is that at the end of a stellar cycle of a star, everything all the atoms at the center start to form iron, because that is the most stable nuclei, right?
That's right.
So, but in a neutron star, the whole star itself is the nucleus of an atom in a way. Is that correct?
You can think of it like that, actually. Yeah. So that's a weird. Yeah, it's super cool. The fact. So one thing was that not everything creates a neutron star. So
Yep.
you need to have stars that are not too small, not too big, somewhere in the Goldilocks for a neutron star. And yeah, they can form these neutron stars, and they are, like you said, just, I mean, they can be thought of as a soup of neutrons. And
Neutrons.
it's just a lot and lot of neutrons, insane amounts of neutrons, right?
Wow.
And technically, you can think of that as an atom, I guess, because an atom is basically, I mean,
Yeah.
Nucleus of an atom is basically that only, right?
yeah. So if you can always switch between a proton to a neutron. You can create different types of isotopes, but you can basically think of it as an atom. Yeah, we thought about this, but I don't know what it means though. I don't even know if it.
So coming to the next question, I always had this doubt from college. Like, uh, in a nucleus, it's a densest, most possible state there is, and in terms of only there is no only Coulombic attraction. They have almost broken the Coulombic attraction. They are as close to each other as possible. But there are objects which are denser than them. Neutron stars will be denser is a black hole. Is that correct?
Yeah, I think that is. Yeah, I think beyond a neutron star,
So,
you can only have a black hole. You
so
can't
I
have
don't know.
the density of.
Inside a black hole, are there quarks? Then, matlab, in freely flowing,
That's the
it's a
question. So, general theory says singularity. General theory says that beyond the horizon, everything just crushes to a single point. So it doesn't matter what that single point is made out of because it has 0 dimensions. It doesn't exist in our 3 dimensions of space, which makes no sense. It exists in a 0 dimensional space, which probably is not true. We hope is not true because that breaks our understanding of the universe. So hopefully general theory is not right in that prediction. But technically, general theory says that beyond the horizon, does it really matter? I mean, you can never get information
any
beyond
information out of that.
Out
So
of that. Okay.
I mean, just everything outside it is well predicted by general theory.
Yeah,
So
interesting.
I
I
mean,
don't know.
it makes sense that well, we can't get any information, so it doesn't matter. But still, we say that these black holes are 10-20 billion size of the 10-20 billion times the mass of sun, and
Yeah,
now we are learning that it's just a singular point. I mean,
it's insane, right? It's
it's
probably not true. It
something
doesn't
a
even.
human mind can't. I don't know. How does he?
just
But the way
makes
I see it, the way I let myself go to sleep, and I think a lot of physicists to make
How do
themselves
you
go to sleep.
study such things?
Uh,
I mean, yeah.
yeah, how do you even go ahead?
So this is a question to you. I mean,
Yeah,
so basically, so this was always a fascination to me. How did Einstein or all those physicists imagine these things? Just staying in a room and they're imagining how the cosmos work. So now you are on the same board. You're trying to think on the same lines. I wanted
yeah.
to ask, how do you train your mind to visualize this? Is it just theory that you guys do, or you need to visualize things also, how
Oh,
things happen?
so obviously, learning about a subject is a lot easier than creating the subject. So people like
Okay.
legends,
All
these
right.
legends had to do they're just insane. They're beautiful. Everybody wants to be like them, and even if you can achieve a fraction of that amazing caliber, it's great. So I don't know how Einstein did it, but after Einstein did it, he
Yeah.
taught us how to do it, and
Yeah.
then how we understand how to do it. And the way you visualize it is you don't look at the big picture because Einstein never had the big picture.
Yeah.
The way Einstein did it is he looked at a simple thought experiment, whatever, there's many thought experiments, we had 3 or 4 thought experiments, but he looked at one of them. He just thought about them. He used a lot of logic. He clearly labeled his assumptions, and then he went forward with it. So he just went bit by bit by bit, and he followed this string, this yarn that took him through this insane physics. And finally, you end up discovering the general theory of relativity. But it's not like you can approach
Yeah.
it at the very beginning. So when you bite it, so that's how we learn it. We learn it bit by bit,
Right.
bite size, and then you kind of end up understanding it. It's still awe-inspiring when you zoom out and think about what you just learned. But when you come back in, it's like, yeah, I can understand that. And that's why I think everybody can very easily understand the special and the general theories of relativity. They're very logical. With university level mathematics, you can do it. With 12th standard mathematics, you can do it. I don't know why we don't do that though. It is actually so simple, and it's just thought experiments. We don't need to look at a
So,
telescope.
you are you talking about special or general? Because
I'm actually talking about, I would argue that general theory is a little bit easier to understand than special theory because it's very counterintuitive in a lot of ways. Like,
Yeah.
simultaneity that you question all that. But I'm getting ahead of myself. The point is, though, I think that both can indeed be taught if we teach them a little earlier. I don't see the problem. I mean, for people who are interested, I'm not saying keep it a mandatory course.
Obviously.
For those who are interested, I would have liked to have learned it, and I know I could have learned it before, and I know everybody else could have, because Einstein did the big deal. Now it's all broken down into bite-sized chunks. Now just start eating them.
now that now that you have talked about general theory of relativity, and I do agree with you that everyone should know what general theory of relativity is. I myself have tried to understand it, never went into the mathematics of it though. But now that we have an expert who's actually studying it a lot closely, can you explain to us what that means? First, let's start with layman terms, and then obviously we'll go deep inside
So obviously, one big clarification. More certainly, I'm not an expert in this. I
it.
am
Okay.
a student and hardly not even good at that. But from what I understand, so I should. So the reason I feel like everybody should be able to understand general theory is that, like you said, you don't need to go to extreme amount of mathematical scrutiny about, I need to understand tensor calculus, I need to understand all that. You will need a very cursory knowledge of that to understand the very basic, basic predictions of general theory. And I think that's at least good enough to at least let people understand a better give them a better feeling of the subject. So, which would bring me to the layman description of the theory. The general theory is called the general theory because it's supposed to describe everything. It's supposed to describe all interactions of matter, energy, and the space and time. And by that, what we mean is it should describe what is gravity, basically. It should let us know what is gravity? Is it a force? Can it be thought of in any other way? And how do we manipulate it? And how do things manipulate gravity? And so I guess I can't give a tutorial on the general theory, but I can tell you some of the interesting results.
Yeah.
I think we can understand. One of the interesting results we can understand is that the general theory of relativity tells us from, well, a portion of the general theory which deals with something called the equivalence principle. There are two types of equivalence principles, but anyway, the result is that we can think of gravity as a force that is exerted on an object. Like I can be sitting in a room which has no windows, and I'll feel, and if I have a weighing scale, and that's the only thing I have, I will see a measurement of my weight. I'd see my weight there. But you can also think of gravity in another way. Imagine rather than thinking of yourself in on top of the scale, imagine that this whole room is being accelerated upwards because of some rockets that you have in space with an acceleration that is equal to that of gravity. So even in that case, when you look at your measurement in the weight, it'll still show the same weight that you are on Earth. And if I close that window, if I close that room and I close all windows, you can't really look outside. You can never make any observation. You can't think of any experiment in which you can be able to tell whether you're in a rocket that is going upwards at the acceleration of the gravity, or if you're being pulled down by gravity. And the reason Einstein comes up with this it looks like a metaphysical kind of a relation, is that from that he will go onwards to let you know that you can think of gravity not as a force, but rather a curvature in the space and time, wherein all particles unperturbed would like to go in straight lines. Okay, it's just that the straight line for the International Space Station, which is technically falling, it has no external forces. It just so happens that the straight line has been curved around itself, and therefore you have an orbit. And that orbit is technically a straight line. It's just that the space-time is curved in such a way that that would be a straight line in that space.
Yeah.
So, Srinivasan, I think for layman terms, can you explain this straight line? Because I understand you're not, as from what I understand, you're not talking about space straight line in a normal space. You're talking the
On a
straight line or
space-time
the
fabric, on the space fabric, right?
shortest, shortest distance on that fabric.
That's right. It's technically called a geodesic. Um,
Hmm.
and Right. I am not talking obviously a circle is not a straight line, and I shouldn't be calling it a straight line. I should be calling it a geodesic. But how do we can understand it as this? Okay, a geodesic can be described as the path that an object would take, given that it has no external forces on it, where you don't consider gravity to be a force. As long as you don't have any rockets that you're throwing, you're using Newton's third law and throwing stuff out and accelerating. As long as you don't have any of that, the path that that object will take under the sole influence of gravity, whatever be that path, is by definition a geodesic. And that path, when can be thought of as the object can be thought of as traveling along that path given some initial conditions like initial velocities. And the effect of gravity is to basically change the direction of that path. So if you add a very heavy object there, that path could initially, if you had no mass, the path would be a straight line. That's why I call it a straight line. Because without anything in space, if you start going in one direction, you're just going to keep going in that direction. You don't need any rockets. You're not going to decelerate. You're going to keep going there. But if you introduce like a star, you're going to start gravitating towards the star.
Yeah, yeah.
The reason we call it gravitating towards the star is because of gravity, which Einstein says, don't think of it as a force, but think of it as that very straight line being curved.
Yeah.
So that straight line is a curved line.
If I understand you correctly and I put it in very simple terms, let's say we have a normal sheet of cloth, okay, and I just push a marble from one end to the other end. Let's say there is no external force. Let's remove every wind and everything. It will go in a straight line. But let's say we had a big ball on one side, kept on that sheet of cloth. Now, if we push a marble in a straight line, it may happen that that ball sucks the dent which we created on that sheet of cloth. It sucks in that marble, and it starts revolving around that.
Absolutely.
To put it, but this is how people explain the space-time fabric, but it's not in 2D. So I think it's very simple. It's in 4D. Yeah.
Yeah, it is. But yeah.
So yeah, fascinating. And Einstein, it still blows my mind how a human mind can think. Like something like this is happening in the universe.
That's ridiculous. And the fact that it was proven while he was alive is, I think he was alive then.
Yeah, he was.
Yeah.
They proved it using, I think, perturbation in Mercury's orbit.
Oh, that too. That is also there, but I think that came later, if I'm not wrong, or it was there in his time. I'm talking about. I think it's called the Davison-Shermer, where they look at the stars. They look at basically
solar eclipse.
Yeah.
And without the solar eclipse, without the sun.
Yeah, I'm not sure if Einstein was there for that, but that was the most visual way to understand that Einstein was right.
But was he? What I have read, if you know about this, there was a rivalry between Einstein and Niels Bohr during this time. Quantum physics, when quantum mechanics actually came into being. So, do we agree that Einstein was right with general theory of relativity, or we have are there some question marks raised, or is it correct?
I'm on team general relativity, so you should also ask team quantum mechanics. Is quantum mechanics, and people have really general theory is about the cosmos and very large scale. So it's very hard to create a lab experiment for them. So you can't do a lot of experiments. You have to keep observing, and you can have all these observational errors. So it's kind of tough to do a lot of experiments on general theory. But quantum mechanics is something that you can do in a lab. We have a CERN detector for that. So quantum mechanics has been notorious for having proven itself right all the time. It has never once. So it's actually the most well-tested theory that we've ever made, which is sad because I find it really tough to understand. And to understand is the general theory. But general theory, it has a singularity, and that is just exasperating for me. Like it's not true. It's obviously not true. I feel like
So like you,
I don't think we have an experiment yet that disproves. No, certainly we don't have an experiment that disproves either of the three theories. But they definitely don't agree with each other. So you can look
Ah,
at the horizon of a black hole and or the singularity. For example, quantum mechanics will not allow you to have an infinite density of a singularity. But general theory says why not? And I don't know if quantum mechanics allows it or not, but it doesn't really like it. So you have a lot of mismatch between the two theories.
yes, yes, yes.
They always fight against each other. We're not able to figure out which is true, but it's probably going to be a theory that's similar to quantum mechanics. That's right.
A unified theory. We are still in search for the unified theory, I
Oh,
guess.
yeah, yeah, we're
Obviously,
getting
we are.
the people who do
interesting.
that are just amazing. I don't know. They don't even see. They don't see anything. They just work with matrices. It's insane how they do that. You have
Oh,
string theory. These things. These are all that.
yeah, string theory and all that. Wow.
So
Uh, hmm.
so I have one question. Sorry. I always I wanted to understand that if say suppose if universe was a box, okay, it was one single box, and yeah, and you throw basically a black hole into it and other stuff into it. Okay. So slowly you can see that black hole will eat away all the matter in that box, and you will end up being a super dense object at the end of this process. So in a way, isn't that decreasing the entropy of the system? I always had this doubt that matlab, I understood that everything in the universe, every process in the universe follows second law of thermodynamics. That is, as a system, the entropy of the system increases at
Yeah.
every as time progresses. That is, I
Yeah.
think, one of the way we define the arrow of time. That as randomness increases, as things become more random and dispersed, that
Yeah.
means time is progressing in the right direction. Sorry, yeah. So
Absolutely.
does black hole all I'm trying to say, does a black hole or body like a black hole uh, violates such principle, or
Well, Hawking had that idea. So Hawking was thinking along those lines, and now this is where I deviate from my field, but the general idea that I understand it to be is that you're right. It appears as if a black hole is sucking everything in, and it's not giving anything out. So this kind of randomness, this entropy that we call, which is basically a measure of motion, randomness, chaos, or basically disorder in a way, or some kind of we can think of it as a disorder or some kind of information that's constantly being increased. And when that information goes inside a black hole, it never comes out. And by information, it could be a photon, it could be some particle. All that information about those particles is just lost. So if I look at a black hole now, I can never tell what particles were there inside a black hole. It's as if a black hole is basically, if you think of a programming language, it's the destructor. You have constructors which create these objects. We have the program which, and this destroys them. And you never get to know what, once it gets destroyed, it gets allocated, the memory gets reallocated, whatever. But that's where the analogy ends. But basically, it makes you lose information about that. And that is indeed looks like entropy goes down, right? Like you said, if I keep a black hole in something, it's going to suck everything in. And then when I open the box, I'm only going to see a big black hole. I've lost so
so
much.
things were disordered and now they're in a compact shell, like it
Yeah, or
feels
they just destroyed, or however you want to view
I
them.
don't know. Okay.
You're right. But then I guess Hawking went along that line and he basically theorized that his own radiation, Hawking radiation, which gives something back to the universe. It takes in all these informations about these particles, but it gives something back in the form of Hawking radiations, which the way I understand it is like the antiparticle of, I don't know. I don't want to say something that's not right, but basically it gives back information, which allows you to maintain this entropy not reducing. And that does helps us not violate the very, very fundamental theory of entropy, which is by far the truest thing amongst all these theories of quantum mechanics and general theory. Entropy cannot be messed around with, I believe. So yeah, so something as fundamental as that is not being messed around with black hole because of Hawking's work and people like Hawking, Penrose, and everybody. So I think that was a very hot topic what you brought up, but I guess it's now resolved, or at least no one's really talking about it too much. But okay, we also have so this is called the black hole information paradox. It's this whole field that we're talking about. We have these you have a lot of complications. And I'm deviating from my field of study, but so far it's not a very clear indication of any theory being wrong. I think you can use a little bit of quantum mechanics and appease everybody.
Okay, okay. Not a big fan of quantum mechanics, I see.
No,
Me
I
neither.
can't understand. I'm too stupid to understand. That's the way.
Me neither, man. Seriously, at bad grades in quantum.
Yeah, man. I actually tried to study because it fascinated me. So I tried to study a little bit of quantum mechanics, quantum physics, but I started to question my reality.
Oh
It
yeah,
is, it
absolutely.
is, I don't know. It's something which is too much to understand.
I agree, man. I agree. And this is
You have
coming.
to, you know what I have seen professor says and what I have seen researchers do, just take it at its face value. Don't try to interpret it in any way. Just these are mathematical equations and this is how it will behave in a given experiment, you know. uh,
Yeah,
Hmm.
no, you can't visualize it,
Visualize
you
it.
can't understand it. You just, these are the mathematically consistent way of interpreting it. Don't stress your brain
I
how it
agree.
is possible.
I agree. I feel like general theory, if you want to explain it, you'll give them an analogy like a person in a box going up and down. If you had to explain quantum
Yeah.
mechanics, the best experiment we have is a cat dying or not dying. That's the worst theory, man. That's the best way you can describe it. So,
Exactly.
so yeah,
It's
the whole
it's
theory is, I hope, bogus. If not, it's a big.
bogus. I think the half of our world is working on
No,
this.
it's not. I told you, it's the most.
तो कंप्यूटर भी आने वाले भाई, क्वांटम कंप्यूटर.
So
Yeah,
yeah,
the future for sure. Yeah.
but yeah. Okay. That was a good insight on general theory of relativity. I'll sure look up on it again and try to understand the maths of it. But is special just totally out of scope? Special
What's a
things.
special theory? Oh, no, no, no. I guess I might have misspoke when I said that special theory is tougher than general theory. Special theory is something you should definitely tackle before general theory.
Okay,
It's just
before general theory.
yeah. But right now, if you give me a problem in special theory, I'll have to spend a little bit more time than I would, spending time to understand a problem in general theory.
Hmm.
Solving general theory problems are definitely tougher because they're very complicated. You have a lot of calculus. But understanding what the question is a lot easier, I feel, in general theory. Because special theory is all about simultaneity being lost. If I shoot the gun and the bullet goes and hits the person in one frame of reference, that's what happens. In the other frame of reference, the person's head let go of a bullet, the bullet went inside the gun, and all that. I mean, I
Hey
don't,
man,
I don't know if I'm telling the right thing. It's really that. It's almost like that. I mean, it's
I
insane.
I think what special theory basically is, it plays around with your, as a human being, your perception of time. Your perception of time is straightforward, which cannot dilate. And when this time dilation happens, and two people have different version of truth,
Yeah,
yeah,
absolutely.
stuff
Yeah,
happens.
yeah. It breaks a very fundamental idea of things happen simultaneously. Like if something happens, if it's 12 o'clock for you, it's 12 o'clock for him. Yeah, that's
Yeah.
true. Events might not sync up that
Hmm, hmm.
way.
Right, right, right. Okay. Just to let's come to our next section and to lighten things a bit. Uh, let's talk about space travel. And now also, it is a hot topic in the industry too. So I wanted to know about your thoughts on space travel. Now, my question is a normal if what the aim of these industries is to commercialize space travel, which means a normal human can dream to, let's say, travel in space in the near future. My question to you is, can a normal human travel in, like, it's not a 1 day or a 2 day travel, it might take months, the loneliness, the homesickness, everything. Can a normal human, are we thinking on these lines?
Hmm. Well, I think months is not a bad idea because I believe like the longest time anyone spent continuously at the International Space Station is this lady who's been there for over 200 days, maybe over 300 days. So she's almost spent a full year, if not more.
Yeah.
So I guess you can, but again, in the International Space Station, you can always talk with your family, right? You can always send messages. They constantly have video calls and stuff like that. If you're going out to space, let's say, well, no matter where we go, we can always send packets of information to and fro. You might have a big delay. Let's say you're going to Mars, for example. Mars is not that far away. Mars is a few seconds of light far away, a few minutes. But it's not too
But
far.
we are not traveling in the speed of light. So let's say human goes on a rocket.
We don't need to. The point is that you can just go in that rocket. Let's say that whole journey takes you 2 years, right?
Okay.
It's not going to be that long, but let's say it took something like that. In that 2 years, you can do what the people at the space station do, wherein they have Skype conversations, or they perhaps send packets of video messages or audio messages. We can have WhatsApp calls and things like this as the person is going towards whatever planet they are going to with Earth. Because light can still travel very fast. So you might have a big delay of like a minute or within a minute, but you can still converse with people. And I think that's the most important thing for any human, right? To be having that a little bit of human contact. It's like doing a long distance with the whole entire planet.
Okay.
It's the biggest LDR ever. And I know long distance relationships maybe don't last more than 2-3 years, but as long as you're within that 2-3 years, I think you're good. Any longer than that, then you should probably send a partner with the person.
Okay, I understand that. But my question to you is, if given a chance, let's say both of you, my question is to both of you, if given a chance, would you travel to Mars? Let's say what is at stake here, right? You can go to Mars, start your own civilization, obviously, or stay at Earth. So would you take the chance of going out actually in space, just the chance to visualize it, or you would just stay on Earth, enjoy the time here? Because we have to start from fresh there. It will be a struggle. So both of you.
Is that a round trip?
There's no
round trip.
No round trip. There's no round trip.
Once you go on Mars, you can never come back.
You have to. Yes, you have to start. You have to be the first one who starts the civilization there.
Well, that's fun.
That's fun, but
fun. You just need to do a lot of interesting activities with the other sex.
Like if you guys have seen Martian, you might have to do agri. You have to become a farmer there. Yeah. So would you would you go up, leave all the luxuries here, just to experience space, or you would like to stay here and just study and watch movies about it? So okay, my question first. Let's say rhythm.
Yeah.
What would you? What would you do?
Obviously, man, if I'm given that opportunity, I will definitely. I think I am just about done with Earth. So, if given that opportunity, why not? I you know what I will do? I will wait till the point that the life on Mars becomes self-sustaining. Okay. Then I will cut off all the connection with Earth, all the telecommunication services, and I will become God there.
Wow. I don't think
I started life on Mars.
Okay.
Who do you tell this to? That's the point. Who do you tell it to? In Mars, who are you going to tell that to?
No, there will be other children, right? I will not go alone. I will bring some embryos and stuff like Interstellar. I don't know. Just kidding, man. Yeah.
Okay, so you would choose to go to Mars?
Definitely.
Okay. Yeah. Rahul, what would be your choice?
Okay. Why are we going to Mars? We're going to Mars for the experience, but also to find another planet, and then we're going to do this whole process of terraforming, where you're going to make it with the terrain, with water and all that stuff. You're going to give it an atmosphere. All of this is literally to make it like Earth, right?
Exactly my point. Exactly my point.
So, I mean, for the experience of the space travel and the street cred or the planet cred that you're I don't know if it's
been to two planets.
Going to be enough for me to leave, Bali or Goa and places like that. So I don't think I leave Earth, but I sure as hell want to be famous. That I am. I would put me in a fix here. I guess, man. Before everything, you usually have these dummy missions. Like you send Laila, dog and stuff like that to go almost and then but come back. So
Yeah.
I'd like to be one of those. I'll go almost to
Okay.
Mars so I can at least experience that.
So you want to experience a space travel, but you don't want to go to a
Yeah, that's
planet and live there. Okay.
yeah, yeah. But unlike Lila, the dog which got killed, I hope they
You
bring
want
me
to
back.
return? You want to return back?
Yeah, yeah,
Okay. Okay.
What about you, Yash?
yeah.
So
Tell me
yeah,
that.
my answer is pretty similar to what.
Tell you what, you'll be the best rapper by far, and
On that
you'll
planet.
certainly be the best rapper in Mars.
But yeah, I think this is a very nice point. You can have, if you're good at any skill, you can be the best. You can be the best one on the whole planet. But
That's true.
yeah, so yeah, that's a point. But uh, I think, like you said, whatever we are gonna be doing there. But yes, to be the first one to actually, you will be the history books. It's it's a tough choice, yeah. But I
Interesting.
think
Delhi
I
Baba आ गया तो.
literally have no. I don't know what will I do. But
You'll be officially the first Martian. You
uh,
want to get into that? You can have streets. All streets can be named Yash Street 1, Yash Street 2, Yash Street Cross 1, whatever you want to call it. But it'll have your name in it.
I think I
No
will.
more entry roads. It'll all
I
just be Yash roads.
I think I will go. I will go.
Okay.
I will go. I literally had my answer was different two
Oh,
minutes
yeah.
ago, but due to but due to some recent points put forward, I think this sounds like a good opportunity. Okay, yeah. So okay, two of us want to go, and one of us just want to do the space travel.
Yeah. That's right.
Okay.
That's what Musk knows to when to call us. Yeah.
Okay. 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 Let's close off this section then.
Yo, man.
Okay.
Rhythm, do you have anything in mind?
So, when we are on the topic of space travel, I also wanted to see that it will be a very interesting next couple of years. I think till the time we will be old, we might see where our species become maybe a interplanetary species. I don't know.
Yeah.
It might be a cool thing, man. Yeah. So
I mean,
just imagine.
there's a neat video on Kurzgesagt which tells you that, as you, like you said, as you become an interplanetary species, what's next? You become an solar system species, interstellar,
Hmm.
and then you can become an intergalactic. Those are actually metrics of understanding how complicated how complex
Civilization is.
we're
Yeah.
getting there. We're shifting. There's a big shift here. We're shifting from, I think, type 1 to type 2 or type 0 to type 1.
Type 0 to type 1. Yeah,
Zero
we
to
are
insane. The
something
fact that
like that.
insane, yeah.
There is actually there is a TV show where it is a peek into the future where uh, Mars has been inhabited. The name of the TV show is The Expanse. So you have Earth, you have Mars, and then you have something in between, which helps in the transportation
Transition.
of goods. Now the show is about the politics. You literally have politics between the governments of Mars and Earth because you need supplies from Earth. So there is a lot of also yeah, man. So it was a peek in the future, and we might
Yeah.
see it. Why not?
The wealth is there to be made for sure. That's there. Imagine having a stock exchange in Mars and then trading from Earth to Mars.
Oh
Insane.
God. Yeah, yeah. Okay.
ठीक है. So, Srinivasan, our next question is regarding the Big Bang. We wanted to understand like how exactly the universe was created. Like I think this is one of the philosophical question everyone has thought about at some point in their life. That how did we
But no one
came
is
into the
clear.
existence?
But no one is clear. Everyone
Yeah,
has a
Theory.
their
vague
own
idea.
convoluted idea, yeah, whatever that is. But yeah, like purely scientifically
Hmm.
speaking, yeah, I am aware that Big Bang is one of the lead contender in terms of how our universe was born.
Yeah,
Yeah, can you share some light on that?
absolutely. Yeah. So, yeah, like you said, Big Bang is certainly one of the leading contenders. I guess there are a few other contenders. I mean, if you're going to go by the population of people who believe it, the number of people who believe it, Then the second highest would be about, how the whole universe 4,000 years ago, within 7 days, God made the universe. But beyond that would be the Big Bang for sure. And in terms of, I mean, if you can choose which one you wish to believe. For me, I don't know. For me, the Big Bang seems a little bit more. So I'm going to choose the Big Bang. And the Big Bang is a good theory, which again I never came up with. So how would I know? But the way basically the way I understand it is that the name, first of all, let's just say the name is a misnomer. It's, I don't know why it's called the Big Bang. It should probably call the uh, big balloon expansion or something like that, which lets you know that it's not an explosion. The way
Okay.
we think explosions. It's not like something. It's not like you had a very dense, whatever you want to call it, that just started exploding and then it exploded into the space around it.
Okay.
That's not what happened. What happened was the space exploded. The space itself started expanding suddenly very quickly. So think of the whole universe, everything that you can ever think of, all the space in it, all that space with nothing in it, the vacuum, all of that was in a very, very small small package, and the entire package started expanding. It's as if the whole balloon started to expand. It wasn't expanding into space; the space itself was being expanded. You can think of it as we're all on the surface of a balloon. Like imagine polka dots on a balloon. And if you make a lot of polka dots and then you start blowing air into the balloon, as the balloon expands into the third dimension, the people on the surface of the balloon, the polka dots on the balloon, start to move away from each other. So for somebody who lives on the two dimensions of the balloon, they would only look at it as the space is expanding in all directions. It's not expanding into anything because they're all two-dimensional beings. They'll just know that everything is moving away from each other. All the polka dots will start moving away from each other. And that is how we should perhaps understand what the Big Bang is. It's an expansion of space and time. It's
Itself.
a very rapid expansion of space and time initially, and then it continues to go onwards. The Big Bang can be thought of, it has multiple stages. Roughly speaking, the first stage is when I think it starts at 10 to the power minus 33, 34 seconds after the Big Bang begins. At that instant, we're still looking at extreme subatomic spaces. I mean, these are 10 to the power minus 30, 34 meters, I don't know, some very small dimensions. That's this dimension of the universe. And at that point, we had something called the inflation, which I'm sure a lot of people have heard of. And inflation is basically the fastest growth, the expansion that we ever had in the whole Big Bang, the whole universe era. And there it went, so the universe kept doubling in sizes within that fraction of that second, 10 to the power minus 34 seconds. It kept doubling in sizes 90 times, approximately. So 2 to the power 90 is the total magnification of that universe, which is insane. I mean, imagine having 90 bits to, you can describe whatever the hell you want.
So
we're talking about an expansion where you go from extreme subatomic particles, smaller than a proton and stuff like that. I mean, the dimension of the universe was that big, to golf size ball, like a tennis size ball. Within almost instantaneously. And then after that, the universe continues to expand, but gradually decreasing in the acceleration.
Is it in deaccel? We all know universe is still expanding. Is it in deacceleration or acceleration? Is it expanding
is it
faster? Yeah, is it expanding faster than before or slower than before?
Initially, it was accelerating.
Okay.
I mean, first the inflation is the fastest in acceleration we've ever had, and then it continued to accelerate, and around where we are right now, it's expanding at a constant velocity.
Okay.
Hubble had come up with, and but that's the current state of events. But we're skipping a few here. So right after the inflation, we wait a couple of minutes, I think, and then basically had this era in the universe, an epoch in the universe called the recombination. Yeah, ionization. Recombination. This was okay. So to describe what happens in between that time, things were so hot. We had temperatures 10 to the power 30, 40 Kelvin. I mean, these are extremely high temperatures. You can't even describe it. It's trillion Kelvin. And at that temperatures, you can do fission, fusion, whatever the hell you want to, but you don't even need to do all that because you actually have just fundamental particles. And these fundamental particles, the temperature is so hot that they fuse okay, and they become a particle and they emit some light, but then that light goes and gets absorbed by another reaction where it creates a fission kind of a reaction where particles they break apart. So
Okay.
what happens is this light, whatever light gets generated, it gets absorbed very quickly, and it keeps happening. It keeps getting emitted, absorbed, and the universe is basically pretty opaque. And by that we mean light is not able to go across. It's pretty dark. It's completely dark at that time. I mean, it's momentarily you have light, but then it goes away. And at that 1 or 2, I don't know how many minutes mark, we have this recombination where finally the universe has cooled down enough. It's like, I don't know, 10 power 9, 10 power, some very high Kelvin, but not as high, where things can remain stable objects as the way they are. So you can still have protons as they are. Just you can have a proton is a hydrogen, an ionized hydrogen atom. You can let them be the way. You can have the electron and proton combine as well. Okay, you can create these
Atoms.
new atoms, and when you can create some of them, that means some of that light can now escape. And finally, we have light that starts to light still. I misspeak there because light cannot have been formed right away. Light is still being absorbed quite at a very high rate even at that point. Okay. It's just that it's starting to decrease.
So
the rate at light gets
you can think that when universe was formed, it started first initial few seconds. It started to expand very quickly. Not the particles, or not like the particles exploded. I think the space itself start to expand, and then during this stage, when particles were the most fundamentals of particles were close to each other, you can think of it. The density of the cloud was too high. You cannot see through that fog. Now slowly, as it is cooling down, now the fog is going away. Now now light can travel in the universe.
Exactly. And at this recombination era, although atoms are being formed, it is still pretty dark. The fog is still pretty dense in that sense. And then finally, when you fast forward quite a lot, when you go to around a few 100,000, around 400,000 years since the Big Bang began, you finally have this era called the reionization, where basically now things are pretty cool. Light can start to leave, and it indeed does. But it does so by causing an ionization reaction between these hydrogen atoms, and you basically create again ions within the universe. And what happens is it's now just about it's just about not it's not as dense enough now so for light to be emitted, to permeate through, and it's not as hot as it needs to be. So finally you have light that starts to progress, not combining with anything else. It just keeps progressing, and that's the signature from as far as we can go close to the Big Bang. And that radiation keeps getting emitted, and with time the space keeps expanding. And what happens is this term called redshift, where these photons, the wavelength of the photons also get expanded, just like how the space expands. And when that happens, these photons, whatever frequency they were, and gamma, whatever, they slowly start becoming longer and longer wavelengths. And if you remember, longer wavelengths means smaller frequencies. And by smaller frequencies, we go from gamma and then progress to X-ray, and then onwards to visible light, then infrared, until finally we reach the microwave. And we are currently at the epoch where those light particles, those photons, are now in the microwave region. They've been redshifted thousands of times to finally be in the microwave region, and that's what we call the cosmic microwave background radiation, because it comes from the cosmos. They're in microwave radiation, and it's a background that's there in all directions because it was from the universe in all directions.
So initially, the light emitted during the child universe, was of very high frequency, like a gamma ray, and very low wavelength, like a very, very, very high energy particle. And because this light has been traveling from point A to point B, and the universe itself was expanding, so it never reaches the point B. So when it reaches point B, it has transformed from a very high energy gamma ray into like a microwave or a radio wave, something like that.
Okay. Is that do we call this phenomena redshift?
Yeah. So there's actually a really interesting, nice video by Veritasium that describes all these red shifts that we see, from Doppler redshift to this cosmological redshift, and you have a few other redshifts, and how they're all the same phenomena. So this would be considered redshift, and basically it means that the light gets redder. So if the light was like blue in the beginning, the wavelength keeps increasing till it becomes from blue, it goes to green to yellow to red, and hence red shift. It simply means that the wavelength is increasing.
Wavelength is increasing.
Frequency is increasing.
So this redshift is this a proof in a way that the distance between 2 points are increasing, or the universe is expanding?
Oh, absolutely. You're absolutely right there. So this was a big thing. Okay, now we can skip to the current universe, where we had this legend called Edwin Hubble, who noticed that what he didn't know then was a cluster of galaxies, but he noticed that what he thought was a specific galaxy seemed to be moving away from him at some particular rate. And he looked at many galaxies within that around us, and they all seem to be moving away at approximately the same rate that he measured. And that rate ends up being called the Hubble's what is it called? Hubble rate, I guess.
Hubble's constant.
Hubble's constant.
But he has a velocity. I think he has just discovered a formula which is equal to Hubble's constant into something.
You're right. Exactly. That's it. So the distance from one point to the other point times the distance times the Hubble's constant gives you the velocity at which it'll recede. So the velocity and the distance are linearly related with each other. And that is telling us that no matter how far you are, you're gonna the velocity at which it is going away from you is going to be proportional to the Hubble's constant times the distance you are from that person.
So farther things are, faster they're moving away from you.
Yes. Oh, that's that's actually a pretty cool thing. So farther things are actually going faster than you. So technically, you can reach a particular distance where h naught, which is the Hubble's constant, times the distance, will give you a number that is greater than the velocity of light. And that ends up... Yeah, you can find that. And that is a 14.5 billion light years, or whatever be the number you want to be. That distance is basically the edge of something called the observable universe. Because theoretically, there can exist matter beyond the observable universe. We think they do. It's just that they're going away faster. They're going so fast away from us that any light from them will never reach us, because space keeps coming in between light. So it's like the light is on a treadmill, and the treadmill is just going back too fast. So the light keeps trying to come towards you, but gets in the end pushed away. And that's the way you can think about this. So we have this sphere called the observable universe. You might have heard of it. It's just because of that. Like you said, it's for distances where the Hubble rate is so high, the expansion rate is so high, the velocity is so high, relative velocity, that it's just going too fast as compared to the speed.
I've heard of this term observable universe, but I think now I understand it better. Basically, because the speed would be greater than the speed of light.
Yeah. And nothing can travel faster than light, not even information or light itself. So you can never know about it. It's important to note one last thing is that the Andromeda galaxy, which is the closest galaxy we have here, or Pluto, which is right next to us, or the moon. I mean, you can try putting Hubble's law on the moon and state that, the moon should be going away from us at this velocity. You can say that. For that matter, why not me? As long as I'm skydiving, I should be also moving away from the Earth, right? I mean, I have a distance between the Earth. Yeah, I should be moving away from the Earth at a particular velocity. So the caveat is that this law applies when the effect of gravity is not really there. So you have to go about gravitational unbound systems. So you can't even look at the Andromeda galaxy or the nearby cluster galaxy and observe this. They'll be coming towards you. In fact, we're on a collision course with the Andromeda galaxy. It'll be long dead by then, but we are going to collide with it. But we're talking about things which are beyond the gravitational bound of the two objects. So they will keep moving apart. And if you were to switch off gravity in one instant, everything will start moving away from each other at that Hubble's law. But we can't switch it off.
Yeah, right.
So, coming to the next question, the next logical question, that is, why? Why are they moving away from each other? Is there any specific energy involved? Why are they moving? What is the cause of this expansion?
Yeah, some serious foreshadowing there by Rhythm there. Indeed, there is an energy. We don't really know what it is. So the usual term that we give to something that we don't know what it is we either call it black or we call
Or
it dark, or
Dark.
different shades of gray. And hence comes the dark energy.
Yeah.
So yeah, dark energy, like Rhythm foreshadowed tremendously, is what we suspect. It's some kind of, I don't know what you want to call it. You can think of it as a negative pressure, by which we mean things, something that's pushing things away, that's pushing space away from each other. Keep in mind, it's not objects that are being pushed, it's the space that they're living in that gets pushed. And we're not sure what it is, but yeah, well, whatever it is, that will be by definition the definition of dark energy. So it's like a term given to something we're not very sure about.
And also, but I believe whatever we can observe, whatever we can see, it's like only 5-6% of what that there is. Rest
Yeah,
everything is dark matter and dark energy.
if you include the non-observable universe, I think that number might go even lower, unless it's a proportionate number. But I think, yeah, you're right. It's a very small number that we end up observing, seeing, touching. The matter that we know, the majority, like 70+%, is residing in dark energy. This energy that pushes space away from each other, and then another 20% is the dark matter, which is matter, which again we're not very sure about. We can't see it, and hence again shades of black. We can't call it black because we have black holes. We use dark.
So, Rahul, just coming to the analogy you gave about general relativity wala space and time, like you gave an analogy, right? Like you can think of it as a surface of the balloon,
Yeah.
right? So general relativity is basically laws that define the behavior on the surface of the balloon.
Yeah,
And
it's basically, yeah, you're right. It tells you how the rubber on the balloon behaves.
and dark energy is basically the dynamics
Person
of
blowing-
how the balloon itself is being expanding.
Exactly. In our analogy, it would be this
Nice.
individual that's blowing in air
Yeah.
and causing the space to expand. But yeah, you're right. There, it would be whatever is the mechanism that causes this, and it is consistent with general theory of relativity. By the way, Einstein is famous to have thought that he included this term by mistake. At that time, he did include it by mistake, but it turns out with time that indeed we need such a term to explain the expansion of the universe. A constant that he added, a constant which later described the cosmology, which is hence called a cosmological constant. And this is called the lambda, or something, whatever it is, but it basically describes the Hubble flow rate, the expansion of the universe.
Okay. Also, I'm assuming like black holes, like these are essentially dark, so we can't see them. So the way we actually analyze them, is it the same way like we did with black holes? The way
Oh,
they
dude,
interact with surroundings.
you're completely right there. Yeah. So, okay, keep in mind, black holes are not dark. Dark is, I guess, a term that's given to describe something we don't know about. It's all
Okay.
haze.
Okay.
Black, I
Okay.
guess.
Yeah. Black is
hole.
like literally black. They
Yeah,
are
you've
black.
gone for it. Yeah, exactly.
Yeah.
So yeah, so like just like you said, before gravitational waves, you can only infer the existence of black holes. Similarly to this dark matter that I had mentioned, this 20% of matter or whatever be the percentage, to detect such a thing, the reason we even thought that it must exist is we looked at something called the Tully-Fisher model. But basically, we looked at the galaxy. Think of a spiral galaxy like the Milky Way, and you'll realize that the arms of the Milky Way are rotating about the center of the Milky Way. And I told you that the center is a black hole. It's a supermassive black hole. But then when you look at this, the gravity is supposed to pull in these stars, and then the stars are like having a centripetal force by gravity that's causing them to go around in a stable orbit. You do all that simple classical mechanics kind of calculation, you realize that, oh, the velocities don't match. The velocity is much too high for the of that galaxy. And the only way you can describe why the velocities, they should be slung, they should have a slingshot. They should be, flung right out. They're going too fast. They have the escape velocity.
Okay.
So to keep them bound within the system, you need to introduce some more matter. But we can see there is no more matter. Enter dark matter. And then you put this dark matter in this halo. We come up with these nice geometries, and you concentrate them at the center of the galaxy. You also concentrate them around the galaxy and things like that. And everything makes sense. They have all these matter that you can't observe. Then
Hmm.
centripetal forces do cancel with the the slingshot, whatever. Everything makes sense. Classical mechanics is happy. But then,
So,
how do you? I
like,
mean, not enough. Like it's like a what is it? It's an ad hoc. You have a jugadu.
Yeah,
exactly.
yeah. Literally, you
Like
needed
a
some
jugaad.
mass. You needed some mass. You
Yeah, you just
invented a new term.
just cook
We
it up.
don't
I
know
think
what this is. We
you can't
haven't
just
seen it,
no,
but
you just you
we
need
need a
bigger glasses.
formulas to be correct, guys.
Yeah, exactly. But then this very
Jugaad,
interesting,
bro.
thing happened. You had this merger of clusters. Okay,
Hmm.
I forget the paper person, which is wrong. Maybe you can add that later on. But basically, we observed these two clusters of galaxies, and let's say there was no dark matter, they should have kind of merged in a specific way. But
Hmm.
instead,
Okay.
what really was observed was these galaxies came, and instead of just merging right away, they actually went apart. They just went by each other,
Okay.
Oh,
by each other, even though they kind of like almost collided. And then the reason,
Oh.
yeah. So now again, one more jugaad came in that see, this is dark matter I was talking about. But one extra caveat is that dark matter is collisionless, which means they don't collide. So it just goes by each other. And dark matter is the majority of the mass of the galaxy. So wherever the dark matter goes, the galaxy goes. It's like a tether to the galaxy. Dark matter is the big boy, and this thing, little child of the galaxy, is following the dark matter. So when the dark matters are collisionless, so the dark matters, they just go by and then they don't collide. They just keep going by. But they are
interesting.
gravitationally bound, so they try to come back. So they have this very interesting mechanics that ends up explaining everything. So that's one more reason why we think dark matter exists. And now we've seen so many galaxies that if dark matter doesn't exist, then like Newton's laws of motions is not right. So therefore, we're very
Oh.
confident of the existence of dark matter. But yeah, dark. Can't observe it.
Interesting.
There are theorized particles. The particle physicists come in and try to give a good understanding, but that deals with quantum mechanics, so we don't want to talk about that.
Yeah, sure.
Nice,
Okay.
man. Interesting. I didn't
Interesting.
know that dark matter was collisionless. I don't know
Yeah.
how
Yeah.
can matter be collisionless. That is so weird. Like,
That's what.
if it is matter, it
Like,
has to
Jugaad,
be.
they're like,
But
okay,
I don't
switch off collisions. You've played CS:GO. When you switch off just switch it off. Let's see what happens. And yeah, it works now.
know.
Yeah.
Interesting. So you
Interesting.
see, he's skeptical about few leading theories. Next will be Srinivasan's theory. Huh?
Yeah, but let's see where that goes.
All right. Thank you, Rahul. We did have a very insightful discussion on science and astrophysics. So, to conclude this talk, I have just one last question to you. I want to ask you, now that you're actually working in this field, what are some of the mysteries that are yet unsolved, but you know, it keeps you awake at night? Something that you want this thing to be solved, some answer to this question. Anything in physics or astrophysics.
So actually, to add to what Yash said, uh, what are the things like in terms of theoretical astrophysics and in maybe some objects, some mysterious objects like I don't know white holes, which we have not yet even seen.
Okay. All right. So, I mean, regarding Rhythm's question, because that's easy to answer, I would really like to see. It's relating to previous question here about space travel. I mean, if we're going to be bound by the velocity of light, then we're gonna do a lot of. We have to make a lot of compromises. Let's say you come up with a rocket that pushes you at 99.99999% the speed of light, and you can reach Alpha Centauri in like in very quickly, which is the closest star, very quickly. Sure, the people will reach that very quickly, and they'll come back also very quickly. But if you go to far enough, stars that you want to visit, and you do this, the people in the spaceship, yeah, they would have to stay there for a year or two. But then, special theory of relativity and the whole thing about this twin paradox and these kind of very interesting phenomenon basically predict that if you do that, the people in Earth continue to age at a faster rate than the people on that spaceship, going at a very high relative velocity. And because of that, you might have spent only a year on that space, going to that star system, and you come back. But in that time, 10 generations have already passed by Earth. Your grandmother is, I mean, forget that. Your your great great grandchildren are dead already. I mean, you basically say bye to everybody in Earth, because when you come back to that Earth, it's somebody else. It's a different Earth. So for to facilitate convenient space travel, I would really hope something like a wormhole or some technology where
Wormhole.
you heat the speed of light, or hopefully, not hopefully, because that's my whole field, but Einstein might be wrong. Maybe special theory is not super right, because special theory has an assumption that speed of light is constant. It's not really proved in that sense, but it's probably right. It's very likely to be right. Um, so yeah, I would hope something like a wormhole or some jugaad, some caveat in the universe ka laws that we can use to our advantage. Um, Now, regarding something that keeps me awake, I sleep very well, man. I don't sleep often. No, I do. Of course, I love it. I guess. Okay, something I work on. I'm kind of passionate about is I want to test GR. I want to prove that it's wrong because it can't be right. As
GR,
beautiful as
general relativity. You want to prove it wrong. You will prove it
no,
wrong.
I don't want to. I mean, I want to be part of the people.
Okay.
Be cool if
Yeah.
I can prove it. But
Obviously, yes.
but at least I want to be able to understand how they proved it wrong. So it's like I want to. That should be the next thing. I think we're really close to that. General
Okay.
relativity, there's a lot of controversial things which have been proven right, but it still says things like infinities and things like that, which are
Mhm.
probably not right. So you can make modifications to GR. That's probably the way to go about it, making modifications to the theory of quantum mechanics and general relativity, and then making something that works like a grand unified theory. But that would really help explain a lot of things. It gets you now. It all makes sense because someone asks me what happens inside the black hole horizon, and I can't tell them. I have to tell them these ridiculous things of infinities, which makes no sense to me. So
Yeah,
that would be the number one thing that we should really look out for. I feel that's the unified theory. It has to be
okay.
it.
It has to be it.
Yes.
Uh, yeah, but I like your first point because I do believe that speed of light is a huge bottleneck to anything. We can't travel we can just, even if we make rockets which are close to that speed, we can't visit other galaxies. So wormhole is the answer to that.
You can see if you can make something that gives you a constant, decent rate of acceleration. Like let's say you get 10 meters per second squared.
Mhm.
Okay, that's decent, man. You can easily do that. We can do much better. Let's say you had 1,000 meters per second. No, not that much. 10 meters per second square, right? Or 100 meters per second. 10 Gs. If you can continuously be at 10 Gs, right? Yeah, you can reach very high velocities with some time, right? Within a person's lifetime, you can reach pretty high velocities comparable to speed of light, which means your relative time, this whole thing where you have special
Yeah.
relativity, kind of it dilates a lot. The time
Mhm.
gets dilated a lot, and you could, I guess, reach Andromeda and things. I've not done any calculation, but it is possible. But the problem is the people you leave behind them
Yeah.
for.
So
As a function,
You are on a solo journey now.
you are technically you are. You will not.
Literally, you are.
Yeah, you are. Yeah, you
but
are.
I don't know. I don't know whether you guys have seen Dragon Ball Z. Usme, when they are traveling in that Super Saiyan comet, that they are training inside, and time I think is
Oh
slower
yeah,
or
that's
something
right. I actually
like
know
that.
this Majin Buu saga. I've seen a little bit of that.
Something like that. Yeah.
Holy shit.
So my question is on that only, that if you are on that ship, if you are on that ship that is traveling at, let's say, 99% of the speed of light, for
Yeah,
you the time taken will,
yeah,
so for you on that ship, the time taken, so we are in the special theory of relativity realm. So
yeah.
as you are on the ship, your time will be much slower than the 1 year it will take for the ship to go and come back. Is that correct?
Yeah, yeah. So that's a yeah. So time dilates with your relative velocity. It's all relative. Keep in mind that's the whole theory. So just as how let's say the rocket was not accelerating, then the person in the rocket can look at the people on Earth and say the people on Earth are moving at his velocity, but in the other direction because it's all
Okay.
relative. There's no global velocity.
Mm.
He could be right. The people on the Earth could be right. The people on the rocket could be right. So it's all relative. But yeah, but they will age relatively. They will agree with that in the end. Because when they come back, once you bring them both to the same position, they will have to agree with their measurements, and they will indeed. It'll work out that way. It's called the twin paradox. It's another thing altogether. But yeah, you're right. Time dilation does happen, and we observe this. Okay, very quickly, you can observe it with the satellites that orbit Earth. the global station, the GPS satellite.
GPS.
Yeah, the what do you call them? Geostationary satellites. They travel at a very high velocity to keep with the the geostationary condition, and they travel quite high up. So there are two things here. One is that they're traveling fast with respect to people on Earth. So you have this whole concept of they're not traveling as fast as the people on Earth. Now that I think about it, but the point is though they are also at a different point on the gravitational well of Earth, and that also has an effect, a very negligible effect, but it does have an effect. And basically, when you consider the fact that the satellite is traveling with respect to us, and the fact that they're at a higher potential well, you end up predicting that their time rate would be different than ours, and that's what we see. We have to fine tune those clocks once in a while, so they all run on atomic time on the Earth, or we all run on the atomic time on that. But they won't match basically after some time. So
Right.
yeah, that's indeed what
Wow.
happened.
Okay. I think we have shared a lot of fascinating information. Um,
True that.
so thank you, Rahul.
Thanks all.
Thank you, Rahul, for taking out time. Uh,
Thank you for having me. This is actually, I enjoyed it a lot more than I thought I would. It's fun. It's fun when a bunch of people just want to listen to you talk and I can talk. So,
yeah.
it's good that you guys like that. Yeah, I
Yeah.
enjoy it.
And you did
Like
try to explain these terms, which are very complex for a normal
Yeah.
mind to comprehend. But
Yeah.
I think we did a good job.
Yeah, we did. I hope at the end of this, people, I mean, you at least, whoever view this, they end up realizing that it's a lot of science is full of jargon, but the concepts are easy to understand for anybody. If I can do it, anybody can. So it's a lot of jargon. Don't let that intimidate you.
Okay. Okay, guys. Thank you. Signing off. Bye bye.
Bye bye.